Hi, I'm Sean Shanley with Veridiant.
And I'm Andrew Grigsby with Veridiant.
And today we're here to talk to you about air source heat pumps in the Southeast. Before we get started though, we would love to get your feedback on today's training so that we can improve for future audiences. We've provided an anonymous survey for you to fill out. If you're comfortable, there are also some questions on there to help us know what kind of folks we're reaching so we can understand who we're training and who we might be missing. This is an introductory course on the upcoming market transformation in heat pumps and should be used to help inform business owners and installers on basic background and to give you a sense of what you should ask for when you're making decisions. Our objective today is to provide you with an overview of the latest information and available resources. As professionals, you'll be selling, recommending, and hopefully installing new high-performance heat pumps for your clients. We want to make sure that you leave here with helpful facts about air source heat pumps. Our goal is for you to be able to identify 3 technical aspects of heat pump equipment, 3 market factors relevant to new heat pump technology, 3 common myths and subsequent facts, and 3 resources that professionals can access for more information when talking to users, businesses, and consumers. These resources come from a number of different places, such as the U.S. Department of Energy. Our agenda today will first go over a brief project introduction, talk about some basic terminology and technology for air source heat pumps, go through a couple myths and the associated facts, talk about market and incentive information, go over relevant code and installation information, and finally wrap up with a brief activity. To introduce the project, we are here today thanks to funding from the U.S. Department of Energy intended to increase the market penetration of 4 technologies: heat pump water heaters, air source heat pumps, electric vehicle charging systems, and residential battery systems. These technologies were chosen because they have some of the greatest potential for energy savings, cost savings, and market growth. We're required to include this statement: the views expressed herein do not necessarily represent the views of the U.S. Department of Energy or the United States government. And now I'll turn it over to Andrew to give us an overview of what air source heat pumps are and how they work.
Thanks, Sean. If there's one key point to this presentation, it's that heat pumps are not stuck at a 1994 level of performance. Everything changes, right? Ace of Base and Aerosmith were topping the charts back then. You remember, right?
I do.
Okay. Like everything else, this technology is constantly improving, with significantly better equipment hitting American markets in the last 10 years. Today's all-climate heat pumps operate at full heating capacity down to sub-zero temperatures without expensive backup heat sources. These models are whisper quiet most of the time, with soft-starting motors, variable refrigerant flow, and variable output. They operate on DC rather than AC power, so they have built-in inverters, like so many modern devices. Think your cell phone charger or your laptop power cord. All climate heat pumps can be ducted or ductless, so they're ready to fit any installation scenario, even locations where only 110 volt power is available or the breaker box is full. I want to stress that as technology changes, it's more important than ever for sales staff and installers to be current and knowledgeable about all of the options. Here's a diagram of the equipment and heat flow of a typical split system heat pump. The word split indicates that there are inside and outside units, those big boxes, separated from each other. But those work in combination to heat and cool the home. In the winter, cooler air from the home enters the air handler via the return plenum to be heated. Instead of passing through a heat exchanger warmed by burning fuel, the passing air is heated as it passes over the same radiator coil used to cool the home in the summer. In the heating season, that coil contains high temperature, high pressure gas, a refrigerant. As the cooler air passes over the coil, it takes on the heat of the refrigerant. The gas then cools and condenses into a liquid. That liquid is then pumped back to the outdoor unit, a compressor that looks just like a typical air conditioner's compressor. There, the gas passes through an expansion valve to relieve the pressure on the liquid. This also cools it dramatically. Because that refrigerant is now so cold, it will absorb heat from the ambient air around the compressor. Lastly, the gas is compressed to increase the pressure and therefore the temperature, and the now superheated refrigerant is pumped inside to the coil in the air handler, and the process starts all over again. In the summer, set the thermostat to cool, and the refrigerant flow will reverse, thereby taking heat out of the home. This is why it's sometimes said that a heat pump is just an air conditioner with a reversing valve, a part that costs less than $200. So there's really no reason to ever buy a single function AC for a space that also needs heating. Maybe you've heard that heat pumps are more than 100% efficient, and maybe you thought that was just a typo. Well, actually it's true, and here's why. It's a basic principle of physics that 1 kilowatt hour of electricity provides 3,412 BTUs of heat via electric resistance. That's what standard heat pumps use for their auxiliary heat. And it's the same technology as a toaster, a hairdryer, or an electric oven. Here's my toaster. I'm making some very good toast with butter and jam. 100% of the electrical energy is converted to heat at that glowing red element. But by moving or pumping heat, a kilowatt hour of electricity used by a heat pump can deliver more than 10,000 BTUs of heat to a building. This is why we refer to heat pumps as more than 100% efficient at heating your home or business. The precise efficiency depends on outside temperatures and the performance specs of the heat pump. So, 300% efficient isn't a typo, and it isn't magic. It's actually the same basic refrigerant cycle technology we've used for well over 100 years, just with the most modern equipment. When most people think of air source as opposed to ground source, often called geothermal heat pumps, they think of something like what's shown here. There's an inside unit, or air handler, the one in this picture is in a vented attic, and the outside unit, also called the compressor or condensing unit. It sits on the ground or on a platform close to the building, or maybe on the roof. This is the most commonly used type of heat pump as of 2025. These models can offer variable output and fairly high efficiencies. Both the inside and outside units are fairly large. The key challenge for standard heat pumps is the extent to which they lose heating capacity at colder outside temperatures. As it gets colder outside, they require auxiliary heat to deliver enough BTUs to the home. This is the emergency or backup heat that folks hate paying for. Usually it's electric heat strips mounted in the air handler, but the auxiliary heat can also be some sort of fossil fuel-fired system. That might be a dual fuel heat pump that basically has a built-in furnace, or it could be a heat pump installed where the home also has a separate furnace or boiler system. Inverter technology, one of the keys to super high performance heat pumps, is often regarded as new, but actually it's been around since the 1980s. Today, more and more inverter equipment options are hitting the market. They are highly efficient and amazingly quiet. The highest performing inverter heat pumps are often called cold climate systems. They can maintain full heating capacity even when outside temperatures are less than 0 degrees Fahrenheit. That means, depending on the local climate, auxiliary heat does not need to be installed for these systems. Also, these models generally require less power, which allows for lower amperage breakers and easier integration into existing electric panels. In retrofit situations where you might want a heat pump to replace a gas furnace or boiler, access to sufficient electrical power sometimes is an issue. So here we're going to talk about the actual heating and cooling potential for the equipment. And I think this is where there's a real breakdown between popular understanding of heat pumps and what they're supposed to do and what an installer needs to communicate when they're providing equipment for the home. The device is created to deliver a certain number of BTUs of heating and BTUs of cooling. And it's printed right there on the manual. So then it's just a matter of determining, well, how many units of heat or cool does the home needs, and will this piece of equipment deliver it? And the heating performance of the home is shown in what we call design temperatures and what that piece of equipment will produce at design temperatures. 47 degrees is where we learn about the tonnage of the equipment. What's a ton?
12,000 BTU.
12,000 BTUs. So this equipment here is, we'd call it a 2-ton, either one of them. We've got the legacy heat pump on the top and the all-climate heat pump on the bottom. So when we look at that 47 degrees, we can see they're both around 24,000 BTUs, both around 2 tons. But the difference is, as outside temperatures get colder, that equipment doesn't deliver the same amount of BTUs. And with the legacy heat pump, if it's producing fewer BTUs of heating via the heat pump system, that's when the auxiliary heat starts kicking in, and that's when the cost to operate goes up. And that's what people have really hated about heat pumps all this time. But look at the all-climate heat pump. At 17 degrees ambient temperature, which in the southeastern US is, that's the design temperature we're after at this climate, it's still producing 24,000 BTUs. It's still a 2-ton heat pump. So if that's what the home needed, we're delivering. Another way of expressing here, you can see, is the coefficient of performance, COP. And it just kind of expresses that same principle as a number or as the efficiency of the equipment. I mean, if you're trying to communicate with a client about will a heat pump do the job, do you think this is helpful?
I think it definitely is. There's a lot of misconceptions about how auxiliary heat works. People call it different things: backup heat, emergency heat, auxiliary heat. I've run into some people who thought that once it got cold outside, you just switched it over to emergency heat, and they got quite the surprise on their bills. So I think for them being able to see the actual numbers and understand the function of the backup heat, it's important to them.
Yeah, a lot of these little details really help the public understand what this equipment can really deliver.
Inverters are the reason that heat pumps have become much more efficient and lead to greater comfort. An inverter runs on DC instead of AC. These DC motors are fully variable or modulating, meaning they can adjust based on the current heating or cooling needs of the home. When there's lower demand, they run more slowly, using less energy. Legacy systems are single-stage AC motors that can only be either on or off and don't modulate. Two-stage systems are able to run at either a low stage or a high stage. Importantly, there are heat pumps for all installation scenarios. For ducted heat pumps, the two main types are slim duct or pancake systems that you see on the left, and the standard air handler that you see on the right. In this case, the air handlers, the inside units, are about the size of 3 pizza boxes. That's a large pizza, of course, for those pancake units. They can be mounted either vertically or horizontally, and with their small size, they can be installed in a variety of spaces. In this case, you can see that it's taking up a very small portion of an already small mechanical closet. When greater airflow is needed, standard size air handlers are still an option, and they'll have a much larger blower fan and therefore be able to move a lot more air. That's what's shown on the right, installed in a conditioned crawl space. Both of these models have an attached outside unit and push air through a duct system in order to heat and cool rooms throughout the building. Now let's look at ductless mini splits, what most people think of when they hear the term mini split. For homes and buildings without existing ductwork, these provide a great way to switch to a heat pump for a lower cost. They come in a very high SEER, and that's the Seasonal Energy Efficiency Ratio, and HSPF, the Heat Season Performance Factor, which is the less often referenced winter heating spec. Just remember that just because it's ductless doesn't mean it's super high performance. There are ductless models with mediocre specs too. But all ductless models avoid using additional fan energy to push air through a duct system and thereby avoid losing heating and cooling to the outside via duct leakage. When serving an entire conventional home with these, the primary downside is that there's more equipment that needs to be maintained, purchased, and eventually replaced. Generally, you'll need a head, what we call the inside unit, in each room. Those heads only come in certain capacities, and much of the time the smallest capacity is still going to be too large for the heating and cooling needs of an individual room, so you'll end up with oversizing. Generally, a ducted system is best for a typical home with lots of individual rooms. The inside units of the ductless heat pumps can be more discreet than those heads that we saw on the last slide that hang high up on a wall. On the left, we can see a cassette style that's recessed into the ceiling. And on the right side, there's a slim unit that somewhat mimics the look and feel of old-style radiators and sits just above the floor. In most cases, it is possible to mix and match the head styles within a home and select the ones that best meet the aesthetics and functionality goals. It's usually also possible to mix a ducted air handler with ductless heads, so a ducted air handler could serve the main part of the house, with a ductless head serving a little use space or space that's somewhat disconnected from the main living space, like a bonus room over a garage. All of these air handler options could work off of one main outside unit. There are also some packaged units that are newer to the market and are in fact heat pumps, even though they may not look like it. They're called packaged because the compressor and the air handler are part of a single piece of equipment instead of being split between the inside and the outside like a standard split heat pump. These can be a great option for homes as well as apartments, especially when there's not existing ductwork in place, or there's limited space for an air handler within the home or for the outside unit outside of the building. This table summarizes all the variables that we've discussed so far, and you can see that there's a heat pump option for almost any situation.
Despite all the technological advances and the financial case for heat pumps, misconceptions about what it's like to live with a heat pump just haven't gone away. We've already touched on some of these topics, but let's talk in detail through some of the familiar complaints about heat pumps and separate fact from fiction. So, first, Sean, I've heard heat pumps blow cold air.
Many folks are familiar with furnaces or old boiler systems, and they may be expecting a heat pump to have those same hot temperatures that you get from those fossil-fueled systems. And in fact, those systems do have a hotter temperature. Furnaces often put out air at the supplies around 130 degrees. The temperature out of a supply from a heat pump is going to be lower, but still quite warm. It'll be around 100 degrees. So that may lead them to believe that because it's a lower air temperature, it's not going to keep their home warm. It's important to let them know that that cooler air temperature is a normal operating condition, and it's something that they should expect, but it will still keep their house warm.
I mean, and sort of related, people say, even if they don't say they blew cold air, people saying, oh, well, so-and-so had a heat pump and they're just not comfortable. Is that true?
Consistency of heat is one of the drivers of comfort, and fully variable heat pumps provide a much better experience in this. Furnaces and boilers, as well as single or even two-stage heat pumps, cut on and off routinely. Variable speed heat pumps that run for longer cycles at lower speeds are going to be quieter and have fewer disruptive starts and stops. They'll provide the most even heat and provide it at a slower fan speed. This is the best comfort, and it's also a quieter system because of this. Additionally, it increases the system life. It's all those starts and stops that are really hard on HVAC equipment. So by having the system run more continually and longer, you reduce that number of start and stops, and therefore the wear and tear in the HVAC equipment. One of the other things that can affect comfort is where the supply vents are located. Sometimes those are the real problem. Supplies ideally should be positioned so they're not blowing air directly on the people living in the space. They should just be keeping the room comfortable without the occupants even knowing if it's running or not, because they're not feeling that breeze. So if new ducts are being installed, the supply placement should definitely be considered as part of that installation, and they should be placed so they're not throwing air on the people in the room. If there are supplies already in place, you can get different grills that will direct the air in different directions, again with the goal of keeping it from being blown on the occupants in the space. Finally, with the DC motor heat pumps, the inverter ones, that blower fan is always going to be running at the lowest speed possible. That minimizes the negative effects of high airspeed while keeping those unevenly insulated and the rooms with different sun exposures closest to the thermostat setting more of the time.
I've also heard that if you have an older house and you want to switch to a heat pump, that you're going to always have to have wiring upgrades. Do you think that's true?
In some cases it will be true, but there's many cases where it won't be true. There will be some houses where that's necessary, but there will also be a lot of houses where you can use the existing panel. In the panel that you see on the slide here, that house switched from an oil boiler that was providing heat and domestic hot water to an inverter cold climate heat pump and an electric water heater. And they were able to do that without any panel upgrade. Because that heat pump just needed a 30 amp and a 15 amp dual breaker, no additional breakers were needed. That was able to fit within the existing panel, and they were able to avoid an upgrade. Because it was a cold climate heat pump, there was no auxiliary strip heat needed, which would have required additional breaker spaces and may have necessitated a panel upgrade. And if space, just physical space in the panel is a concern, there are some heat pump systems where the air handler inside is powered by the outdoor unit, so you can reduce the number of breakers that way as well. Of course, there will be those cases where a panel upgrade is needed, but it doesn't have to mean that a heat pump's not an option. There's a new 30% tax credit worth up to $600 for a new electric panel. And then there's what's called the HERA rebates, which include up to $4,000 towards a new electric panel.
One last question, and I deal with clients in their homes all the time, and they're wondering, well, what's cheapest? So will heat pumps be more cost effective to operate compared to other options?
Besides comfort, a lot of persistent misconceptions about heat pumps relate to the cost of relying on them versus gas, propane, or oil heat. It's true that 20 or 30 years ago, when the efficiency of those systems were significantly lower than today, they were much more expensive to operate. Today you can find very high efficiency heat pumps. We're talking about an HSPF, the heating efficiency over 12, and a SEER over 26, compared to historically an HSPF around 7 and a SEER around 10. And the COP numbers that you showed earlier help to tell that story as well about how efficient they are. At today's gas, propane, and oil prices, these high-performance heat pumps are going to be much easier on your wallet. Note that these are national averages that you're seeing in the table here. Local prices for electricity and various fuels will vary, but the equipment choices are the same nationwide.
Okay, so that's an overview of how heat pumps work and of their performance improvements over the years. Now let's talk about how those factors and others are affecting the market for heat pumps more broadly. So there are lots of choices when it comes to heating and cooling equipment. Heat pumps of various types, all kinds of furnaces and boilers using a range of fuels, wood stoves, etc. With existing homes, a lot depends on whether the home has ductwork, hot water pipes, or a chimney. One thing we can generally assume is that the home will have electrical service. Given that, it's prudent to ask about paying for additional fossil fuel infrastructure and monthly service fees if it's no longer needed. This chart from the U.S. Energy Information Administration shows trends in retail gas prices since the 1980s. As you can see, after remaining remarkably stable for more than a decade, methane gas prices started creeping up with the onset of the global COVID pandemic. Then, global price shocks caused by Russia's invasion of Ukraine made wholesale gas prices triple, and the entire world market started changing dramatically. Prices have come down since that peak. But now, the relatively high cost and historic volatility of oil and gas motivate many folks to go all electric. That is, if the convenience, safety, cost, and performance of the electric equipment isn't reason enough. In a way, electricity price trends are similar to gas. Here, you can see that same spike in 2022 because so much electricity is generated by gas-fired power plants. Going forward, we expect electricity prices to be ever more stable as it transitions to renewable energy sources. That's because solar and wind power have no fuel costs at all. They are not so vulnerable to changes in the global market. But what does all this mean for buildings, and specifically homes? Well, based on U.S. Census data going back to 2005, electric-only homes continue to gain market share across the entire country. As of 2015, 25% of the U.S. homes were all electric, and in the Southeast, nearly 45% of homes are all electric, which makes heat pumps the kind of obvious choice for heating. In new homes, it's just cheaper to forego the gas hookup and monthly service fees. For retrofits, most ducted air conditioners installed in space that also is heated could be upgraded to a heat pump at relatively low added cost compared to just replacing that AC. Plus, you'd get great efficiency gains. If more customers chose a heat pump whenever an AC was going in, that would more than double the current market share. Here are more recent data on all electric homes, broken out by state, so you can see more detail about how the Southeast leads the country in this trend. Washington State has lots of cheap hydropower, and in Hawaii they don't really heat their homes. I'm not sure what's going on in Arizona. Overall, these trends can be summed up in one word: electrification. As technology improves, energy markets change, and new energy sources become available, the economic and technological arguments for all electric homes just pile up. So what we see is the entire country moving towards all electrical systems. The grid and buildings are increasingly powered by renewables, both on-site and off, which have minimal operational costs and no rising fuel costs, plus no greenhouse gas emissions. Fossil fuel infrastructure will just keep getting more expensive to maintain, especially as users defect for all-electric solutions. As I mentioned, when electricity prices rise, it's generally due to rising gas prices. And again, renewables offer steady costs because there are no ongoing fuel costs. So electricity offers greater price predictability for all consumers. Finally, increasing awareness of indoor air quality risks from gas appliances also cause many folks to shift towards all-electric.
Here's a little more on cost effectiveness using data from the 2021 study released by NREL, the National Renewable Energy Lab, run by the U.S. Department of Energy. The savings from switching to heat pump heat are averaged based on replacing a variety of other home heating systems, from electric baseboard to methane gas. Note that these costs do not reflect the price increases of 2022, where electricity prices increased because some gas prices went up a lot. But you can see how the numbers add up. If consumers can pay a little bit more upfront, they'll save thousands over the coming years. Note that this is for a replacement system, where the ductwork is already in place, and the choice is whether or not to replace a functioning heating system. For new construction, all-electric systems are cheaper from the start, because you don't have to install the additional infrastructure of a gas line, and you don't have to vent any fumes. There are some important new incentives as well. They're available now and being rolled out in states across the country. The Federal Inflation Reduction Act of 2022 boosted the tax credit for high-performance heat pumps and established the Homes and Here program. The 25C tax credit, available to any household that pays federal income tax, is worth up to 30% of the consumer's turnkey installation price, with a cap of $2,000. So if you spend $8,000 on the job, you'd get $2,000 off of the taxes that you owe. And you can use this credit more than once. So if your home has 2 systems to upgrade, you can stagger that work, replace one system this year, replace the next system next year, and then you'd be able to use that tax credit twice. One important detail is that the credit is only good for very high performance models, so 18 SEER or higher and 9.5 HSPF or better for split systems, and ductless systems require an HSPF of at least 10. That's what the CEE highest tier note refers to. And you can expect the specs for meeting that tier will continue to get more stringent over time. But that's good, because the highest efficiency equipment will save folks the most money over time. The Homes and Here programs are quite a bit more complicated. Each state will design and implement its own version of these rebate programs on its own timeline. Once launched, Here can provide up to $14,000 in point-of-sale rebates to consumers, and Homes can provide rebates up to $8,000, with maximum amounts going to lower-income households. So stay in touch with your state's energy or housing department to get updates on the details for your area and to see how that rollout process is going. Because the federal incentives refer to it, let's take a minute to cover one important technical detail regarding how we talk about the efficiency of heat pumps. As of January 1, 2023, SEER 2 and HSPF 2 are the new efficiency metric standards for heat pumps. The main difference between the old and the new ratings are the testing conditions for each of those rating systems. The new testing conditions will produce different data values, and they warranted a new rating system. So for SEER 2 and HSPF 2 ratings, the testing procedure increases the pressure conditions to make them more like what you'll see in an actual ducted system in the field. As a result, the SEER 2 ratings for cooling equipment will be a bit lower, about 5%, than SEER ratings in most cases. And similarly, for heat pumps, that HSPF 2 rating will also be lower, about 15%, than the HSPF ratings. For example, a heat pump with a SEER rating of 14 and an HSPF rating of 10 would likely get a SEER 2 rating of about 13 and an HSPF 2 rating of about 8.5. The difference between SEER 2 HSPF 2 ratings from SEER HSPF ratings will vary from one equipment to another, but it mainly depends on the system type, such as split system, single package, etc. Here's a bit more detail on those federal incentives. The 25C also includes a 30% tax credit for work on the electric panel in the home, with a cap of $600. And note that the HERE program also has a rebate for electrical upgrades. These would be subject to the overall cap for the program per household, and the formulas are a little bit more complicated. I think the main takeaway is that homes adhered together could provide several thousand, even more than $10,000 for low-income homes, towards home energy improvements, including high-efficiency heat pumps. In Virginia, there's been legislation in recent years that is prompting our electric utilities to offer various rebates for efficiency improvements, including upgrading heat pumps. Note that this does not cover a fuel switching scenario where a heat pump would perhaps replace a boiler or a furnace. It's only for replacing existing electric heat, and that could be either resistance heat like electric baseboards or a heat pump. You can see that the rebates aren't large, but this may change in the future. In Florida, some electric utilities offer rebates for HVAC improvements, including upgrading to heat pumps. And that includes Florida Power and Light, Duke Energy, Tampa Electric, and Florida Public Utilities. Choosing an inverter heat pump opens up a significant savings for the customer. If they make 80% or less of the area median income, they'll only end up paying 36% of the original installation cost once the rebates and tax credits are factored in. Someone making 80% up to 150% of the area median income will end up with savings almost 40% off that original installation cost. But if you install a legacy heat pump, they'll see no savings. Even if you install a highly efficient furnace, at least 97 AFUE or higher, they could only save $600. If a customer has older equipment, say an existing heat pump or furnace, and it's in need of repair, the available incentives can make replacement with an inverter heat pump much more attractive than repairing. Code requires that all HVAC systems, including heat pumps, are designed and installed in accordance with industry standards for calculating the sizing, equipment choice, and duct layout. Here we see a diagram showing the 4 key manuals from ACA, the Air Conditioning Contractors of America. The manuals are books that software packages are then built off of that get into all of the engineering details such as heat movement, airflow, solar gain, etc., to precisely calculate the home's heating and cooling demand, select equipment based off of that, and then create a duct layout that's best going to help the home meet those loads. It starts with sizing, and that means selecting equipment with heating and cooling output that matches the needs of that specific home. Just choosing equipment based on square footage or that seems to be, just a little bit bigger just in case, it's not smart. Oversized equipment costs more to install, it doesn't dehumidify as well, and it wears out more quickly, both of those things due to short cycling. Short cycling means that system kicks on, it runs for a very short period of time, and then turns off. For heat pumps that will be installed without auxiliary heat or other backup heating systems, you'll also need to consider sizing for both cooling and heating. Typically, we size for cooling. With those specific system types, you also want to take into account the heating needs. Please don't make the classic mistake of installing oversized equipment. It's the pathway to poor performance and high cost. Use the software that's available. Using the software also definitely applies for existing homes. It's not just for new homes. Just duplicating the capacity of an existing system in an existing home may give you the right answer or it may not. It's highly likely that when the existing system was installed, it wasn't sized using the Manual J, and there have likely been improvements or changes to the home itself, such as air sealing, insulation, windows, other energy efficiency measures that may have occurred since then as well, which would impact the size equipment that that home needs.
There are, in fact, fewer code requirements that relate to heat pumps compared to a fossil fuel system because you're not installing a combustible gas. You don't have to worry about providing combustion air, and you don't have to worry about venting fumes. When installing split systems, where there's the air handler inside and the compressor outside the building, you should consult local FEMA maps to make sure that the outdoor unit is safe from flooding. Many homes and buildings mount outside units on platforms well above grade, and this can be in response to flooding or maybe it's security. And sometimes they have to be elevated because of steep slopes next to the building. When thinking about where to locate the inside unit, heat pumps offer much greater flexibility compared to fossil fuel equipment. They come in different sizes and styles, as we've discussed, and they don't require the venting of fumes. I will say that whenever at all possible, we do want to install the air handler and ductwork in conditioned space, not like that one shown in the middle, which is in an attached garage. and that principle would apply for fossil fuel equipment as well. Ideally, an electric panel upgrade won't be needed before a heat pump can be installed, but it may be necessary, or the homeowner may want it done at the same time. If the homeowner would prefer not to upgrade the panel, an electrical load calculation can be done using the NEC electrical load calculation form for a single-family home. ACA, the Air Conditioning Contractors of America, provides a detailed guide to quality HVAC installations. Following these best practices will optimize efficiency, power consumption, comfort, and equipment life. ACA Standard 5 is straightforward and gives a good number of options for performing each task, and it has guidance for new and existing systems. So, lastly, we're going to talk about a real-world example, which in this case is a retrofit situation of putting a heat pump in a home that did not have one previously. Here's our case study house. It's a 1950s ranch, about 1,000 square feet. It's in Richmond, Virginia. It has a functional oil boiler and uses window units for cooling, but the homeowner complains that the boiler is noisy. It's situated in a closet in the middle of the house. The homeowner also says the radiators are noisy because they pop when they heat up and cool down. Most importantly, these residents want to get off of oil. It's dirty and expensive, and they want to get rid of the window air conditioners. They're hoping to get a system that will be quiet and less expensive to operate. But, as always, the first concern is cost. If we're trying to make these changes to this home, what options, Sean, would you present to the homeowners? I know this happens to be your house and you acted as the contractor. So, where do you start?
Some of the considerations, if I were an HVAC contractor, that I would want to take into account are, does the client have a specific equipment preference? Are there specific problems that the client is looking to solve? Are there any existing ducts that we would be able to reuse? And what equipment will physically fit in the space? That's often a large constraint with existing homes. So this is the layout of the house. The house is on an accessible crawl space and it has an attic with pull-down stairs. So the first decision point is, do we go with a ducted system or a ductless, since this house doesn't already have ducts? So if we're thinking of possibly going ductless, then the next question is, how many heads do you need to install in this house? Personally, I'd probably be leaning towards 5 heads. The smallest capacity for most manufacturers is 9,000 BTU. For some, you can find 6,000 BTU. If you end up going with that standard 9,000, then you've installed 45,000 BTU of capacity, which, having done a manual J calculation, is over twice what's needed. While the equipment is variable capacity, it's a whole lot of extra capacity that the homeowner has to pay for. It also introduces a problem of likely not having enough moisture removal ability. If you're in the ducted camp, which makes more sense looking at the specifics of this home, then it comes down to where do you put the ducts and where do you put the air handler. In this case, we can choose either the crawl space or the attic. The crawl space, we're able to have conditioned space down there. It's an encapsulated crawl. While it was very challenging to physically fit equipment in there, that did end up being the best choice in this house, just to keep everything within the thermal envelope, which also helped to reduce the size of equipment that was needed for this home. Again, remember that there are tax credits and some additional rebates available, so it's beneficial to work these numbers in as much as possible to help the homeowners out with that initial cost. One issue is that for the tax credits, the homeowner is still going to need to pay that cash up front or get credit up front, because they won't see that until they file their taxes. Whereas with the rebates, you can get those pretty close to the time of the install, but those are much smaller dollar amounts.
Well, that's our presentation. As we noted at the beginning, we really would appreciate your feedback so we can keep making these presentations better. Here's the QR code you can scan to provide us with anonymous feedback. Thank you for your time today. I'm Andrew Grigsby with Veridient.
And I'm Sean Shanley.
And good luck installing high-performance heat pumps.